form better long-term memories. Entirely unexpected to me, putting us in a completely different field and showing the beauty of serendipitous discovery that comes out of curiosity-driven research. There are some profound implications from this simple result, and that is that these are normal mice, right? That we can enhance their cognitive function. So there must be a break normally on. Evolution hasn't optimized this process, and there's an extra reservoir and cognitive capacity that can be tapped into, so this molecule can release this break. So the question is, can we exploit this increase in cognitive capacity in disease? We collaborated with Susanna Rossi's lab at UCSF, who has a model. Susanna has a model of traumatic brain injury, where we basically test mice here in this assay, in this water maze. So the mice have to swim to this hidden platform in one of the arms. They orient themselves with visual clues around the room, the same way we will have to orient ourselves on the Stanford campus here. And we basically train them in this task, and we measure the time, and we measure the number of errors the mouse makes swimming into the wrong arm. And this is the result here. 2 weeks later, when we look how much do they remember about what they've learned, control mice make, on average, 1 mistake, whereas mice that have received this brain injury make 3 to 4 mistakes, and that's basically a random exploring. So they don't learn that they're permanently demented in this situation. If we inject the drug, the amazing result is that these cognitive defects are entirely restored. So this gives us hope. So ISRIP corrects the cognitive defects after brain injury, even if we give the drug 4 weeks after the injury has actually been inflicted, and these permanent cognitive changes have occurred. So these results open new paths to how memories are stored and lost, and they allow us to think about potential therapies in diseases which have cognitive defects. In addition to traumatic brain injury, we have many of the neurodegenerative diseases that are connected with cognitive dysfunction. And then as it becomes increasingly apparent to me, there's also a process that occurs with aging. So hopefully the development will keep pace with us getting old. This is of course fantastic news for all the mice in the audience. We have no idea whether any of this will translate into human physiology. Mouse brain and human brains are quite different, but as I said, we are quite hopeful. So that brings me to the end here. What we try to do then strategically is to understand the precise molecular mechanisms that control the fate of cell proteins. We would like to modulate these mechanisms in various disease models and translate then our knowledge from animals to humans, and then assess the safety and utility for therapeutic interventions in various clinical trials. And this is sort of a continuum between academia and biotech, where the collaborations are incredibly powerful, especially in the middle range of this, and we have very good connectivities in the Bay Area here to push this to the next step. And the dream is that we will use this knowledge, we as a field, to develop new cures, novel cures, for many of the diseases that I mentioned to you, for cancers, cognitive disorders, and other diseases, by targeting these Achilles heels of cell quality control going awry, and develop preventive measures that keep our proteome in cells healthy, and therefore nudge our society a little bit more from the current strategy of basically dealing with diseases as they occur, to become more proactive and preventive, so going from sick care to health care. Schiller used this, Friedrich Schiller, a German philosopher, used this beautiful word, edle Wissensbegierde, so the noble quest for pure knowledge, which sort of describes beautifully what we do in terms of curiosity-driven research. We started our work as entirely disease agnostic, and the broad spectrum, I think, justifies it. It touches many different ways. It was not predictably translational, yet our funding agencies ask us to justify what some of our knowledge will be useful for in the long run. And finally, it is entirely open-ended what we do. There is no end in sight. And this is a wonderful future ahead here of discovering more. And because it's open-ended, there is room for all the young people entering the field. As Einstein said so beautifully, as the circle of light increases, so does the circumference of darkness around it. And of course, it's in that range of darkness. The more answers we get, the more questions we generate. And it's in the circle of darkness that all the next generation will find their careers and make new discoveries. With that, this is the work I'm being honored here for, is of course I have to credit the many people over the years who've worked and dedicated their work in the lab, and the large number of collaborators who so generously shared their expertise with us. Thank you so much. Excellent. Some time for questions. Can we take you right there?
Sorry, I have two parts. I'm really curious about what your current working hypothesis is for how the ISRIP drug affects cognition. And I'm also curious about what is it that Sonnenberg said to you that gave you the clue to go and investigate the same?
Yeah, so let me start with the second question. So Nahum had done, Mauro Costa-Mattioli was a postdoc in Nahum's lab, and did genetic work, that the very process that we've been affecting with the drug here is also affected and gives cognitive advantages in heterozygous mice that partially block this pathway. The pathway that's being affected here is a translational control pathway, by which the phosphorylation of the translation initiation factor, which under certain stress conditions inhibits protein synthesis, is now alleviated by overcoming the negative effects of the phosphate being added to the ERF2. We think that then translates into the protein volume, the composition of proteins in these neurons that are affected now in the learning process, in a way that synaptic plasticity is being affected, and that basically you are able again to form stronger synapses. And that of course goes all the way back to Eric Kandel, who showed that learning in aphasia requires active translation to go on.
Hey, Peter, I have a question for you. And I was just wondering, what is the relationship between the death pathway that's caused by unfolded proteins generated from the ER with the mitochondrial, pathways that cause cell death?
Yeah, so the activation of the unfolded protein response leads to activation of the apoptotic program in the cells. If we unfold proteins in different compartments, such as the cytosol, we also affect the unfolded protein response, because now we're backing up degradation systems, and therefore proteins that normally get folded in the ER but misfold, they are shipped back into the cytosol for degradation, and in that case now